So, we were discussing about the circle diagram of an induction motor where only rotor parameters are considered. This was this thing. So, the conclusion we draw is this one. Applied voltage is constant, rated value mind you, per phase, and this is your I 1 which is equal to I 2 dashed. There is no difference between these two, and we finally got that okay, if consider this along this y axis we draw the voltage phasor, then current phasor will be a circle like this. Okay. This is the current phasor. The diameter of this circle is of course V by x 2 dashed, that is there. Then at s equal to 1 standstill condition you draw a line. This is the thing. It is on this perimeter of this circle, tip of the current phasor drawn from the supply will lie. So, it is at this point I called it point S and I dropped a perpendicular here M. This point I just called O, and I showed that this SM is a measure of air gap power as well as rotor copper loss at S equal to 1, because this is S equal to 1. Now, when the machine will be running and SM therefore represents both rotor copper loss as well as torque developed in the machine. Mind you, machine is not rotating, you have blocked it, but it is experiencing that torque. If someone wants to hold the rotor with applied voltage, he will feel the punch of that, okay, it is trying to rotate, you are obstructing that. That is true. But it has developed torque, but you are not allowing it to run. Therefore, no question of any output mechanical power comes in, and NR equal to 0, that is why slip is equal to 1, that is the thing. Now, when the machine will be operating at a general operating point with slip S, it was S equal to which is less than 1, then you just drop a perpendicular here. Call it N and call this point as G, just like that. Then I have shown that the total input power at this slip is Pn, Pn is total input, total kilowatt input. Also I have shown that Gn is the rotor copper loss. This length will also represent rotor copper loss at this slip. Therefore, Pg, which is nothing but Pn minus the Gn, total kilowatt input, and this also happens to be the air gap power PAG, because there is no stator copper loss, this is the power which has gone. So, Pn minus Gn is Pg, must be giving you the gross mechanical power. Output. That was the last thing I told, and we have shown that. So, this one, and for obvious reason, you know, this Gn must be equal to S into Pg, Pn. P S into Pn. Pn is the air gap power, that is S into Pag, this I know. So, Gn, this will be S times the whole length, and the things is over. Therefore, you see this vertical inception, if it operates at this slip, draw a vertical line, this will be the copper loss at that slip, and this will be the mechanical power output. Therefore, this vertical interception between the perimeter and this line, which corresponds to standstill condition line, that intercepts gives you the mechanical power output. That is why this line is often called output line, output power line. If somebody says machine is operating at this point, draw a vertical, this will be the copper loss there and this will be the mechanical power output, very simple. This way we can find out the performance of the machine. So, whatever is the input power, only loss taking place inside this machine in this simplified equivalent circuit is the power loss in the rotor resistance I square R2, and therefore, remaining power will appear as mechanical power input. So, instead of, so somebody says that I will vary the slip between this and this point, for different values of slip you calculate that. So, once for all you draw this circle diagram, decide what is the value of this slip, fix up this point, because power factor angle can be calculated. From that I will fix up the operating point there, and everything, only two things can be found out and I have found out. For example, efficiency of the machine will be this mechanical power output, Pg by Pn will be the efficiency of the machine at that time. For example, efficiency will be output power, mechanical power by Gn. Something like that can be done very simply. Acha. Now, let us take because all things cannot be neglected. This is okay, it will give you some indication, but if you want to get more accurate thing, then perhaps you should not neglect all the parameters of the stators. Now, at this point I will, before I go to the circle diagram of that original equivalent circuit, I will once again reiterate. Once I perhaps drew the power flow diagram of the induction motor, I will do this. We already know power flow diagram. Let us revisit it in somewhat detail. I told, see, in the induction machine I now know the exact equivalent circuit is something like this, R1 X1, then there may be rotational losses, resistance will represent. Last time we were doing this, and this is x2 dashed and this is R2 dashed by S. This is a more exact equivalent circuit, this is the applied voltage, this is R1 X1, all parameter values are there, and this is that R naught or whatever it is, Xm, magnetizing current. Now, in this case, if I strictly go by this, I should draw the power flow diagram in this way. Power input, this is suppose power input, P in. First I find there is a stator copper loss. I will go on subtracting the losses. So, P stator copper loss. Then you see there is eddy current loss, P core loss. Therefore, P in minus the stator losses, and then whatever power is here, that is PAG, air gap power. And from air gap power you have to subtract the rotor copper loss, P rotor copper loss, which is always true that it will be S times PAG. That is all. S into PAG will be the rotor copper loss. Then whatever power you get, this power should be called P gross mechanical. Then after this, if you subtract a small mechanical loss, then whatever power you get is the P net mechanical. This is the exact thing, no doubt about it. Input power, subtract stator copper loss, core loss component, then the power enters, remaining power enters into the rotor, air gap power crosses the air gap as if and enters into rotor. From that you subtract rotor copper loss, which happens to be S times PAG, and this mechanical loss is 1 minus S into PAG. We have done several times, and from that if you subtract a little bit of mechanical friction, windage losses, etc., bearing loss, then the P net mechanical is here. And efficiency of the motor is P net mechanical, mind you, divided by P in. This will be the net mechanical power output. Now, sometimes you will see a little bit of variation in this power flow diagram because of convenience. What do I mean by this is this. Suppose there is an induction motor, listen this point carefully. Suppose an induction motor is there, it could be cage or slip ring, whatever it is. This is the rotor. I have given supply. First thing is, suppose it is running under no load condition, and suppose you have connected some 2 watt meters to record what is the power drawn. Two watt meter method of measuring power. Suppose I have connected 2 watt meters to record how much, and this is the 3-phase side which is excited, 3-phase supply. Now, the question is, when you excite this, what this watt meter is going to read? Let us take from the practical point of view. Here is an experiment. I am running the machine under no load condition, means there is no opposing mechanical torque. Is it true there is no opposing mechanical torque? Not really. There is opposing little bit of frictional mechanical torque is present, that is there. And watt meter is going to read then what? So this part is not there, and then slip has to balance only the little bit of frictional torque present. Therefore, slip will be very small, very close to synchronous speed it will run. If that runs, people say under no load condition slip is practically 0. You are given this liberty, okay, it is very close to 0, so that this part will become open circuit. Therefore, whatever current is drawn from the supply will be magnetizing current and this core loss component of the current. Strictly speaking, the sum of these 2 watt meter readings, even under that condition, that is at S equal to 0, means circuit is like this. You can assume this to be open circuited. So, nothing. So, V 1, this is the no load current I naught, total current drawn. Therefore, I will say the sum of these 2 watt meter readings must be equal to I naught square into R 1, is not. Similarly, there will be power loss in this resistance. R1 X1 is small, okay, approximately same voltage comes close to that. This divided by this R will give you this power. But wattmeter, this is the only points through which power is inputted into the system, and wattmeter should read, and there is a little bit of mechanical power output in the form of loss. Therefore, wattmeter, some of the wattmeter readings will record stator copper loss, core loss plus the rotational loss, that is the mechanical loss, that is sum of wattmeter W2 should be strictly speaking equal to I naught square into R1 stator copper loss plus P core plus P mechanical loss, and it is under no load condition, net mechanical power output is 0, there ends the matter. So, strictly speaking it should be like that, but the no load current is small compared to the full load current of the machine, like a transformer. Therefore, majority of this right hand side will come from this sum of these two, P core plus P mechanical loss. This can be neglected because of what? In compared to the sum of these two, this will be less. Why it will be less? Because I naught is less, no load condition. Therefore, sum of these wattmeter readings will be equal to P core plus P mechanical loss. Both of them are small, but bigger than this I naught square R1, that is what I am telling, but these two are of will be of the similar nature, because in induction motor eddy current loss do not occur in the rotor iron bodies, only in stator iron body it occurs. In the rotor it occurs, but the frequency is so small it can be neglected or things like that. Therefore, these two loss together is called P rotational loss. Well, right now it cannot be separated. I cannot say how much of it is rotational, how much of it is frictional. But anyway, induction motor from no load to full load condition, no load to full load condition, mind you this statement, change in speed is how much? Very little, 5% sleep, little change, maybe 70-80 rpm from no load to full load. Do you think because of this frictional loss will change? No, it will practically remain same, because against air it is running, bearing friction will be similar. I mean, why there should be difference? Because speed variation is less. So, frictional loss remains same. Do you think the core loss too will change substantially? No, because of the fact, although no load current and full load current, they will be different. They will be different by substantial amount, the magnitude order of the current, but nonetheless R1 X1 is itself is small quantity. Therefore, the flux produced by the machine is decided by this current, whether it is under no load. In no load condition, this V1 practically appears here. I naught is small, R1 X1 is also small, no problem. At full load condition, it is running with some sleep. So, this current has now come up, which was otherwise open circuited, will now come here, and the sum of these two currents will flow. This current will increase because you are taking mechanical power output of the machine. So, this drop will increase, but not by a very large amount, because of the fact R1 X1 is also small. So, people say that from no load to full load condition, the level of flux also practically remains same. Therefore, what is the conclusion? Conclusion is this rotational loss, which is sum of these two P rotational loss, which is sum of P core plus P mechanical loss, can be assumed to remain constant from no load to full load operation, no load to full load operation. It can be assumed to remain constant. So, this exact is this. So, sometimes what people do, I mean there are various versions of this power flow diagram, but there should be logic attached to each one of them. So, in the power flow diagram we then find P core loss is here, P mechanical loss is here. They cannot be separated as such by this simple means. If time permits, I will tell you some experiments can be done to separate them out, but in general there are some matters. So, what people do, they will be saying that okay, this is input power, I with a single line I will draw P in stator copper loss, of course, will be there, P stator copper loss. Then you say that there is rotational loss, not core loss alone. Okay, rotational loss I will take right at the input, rotational loss. For that you will be making some mistake, because this is the exact thing. A little mistake does not matter. So, P rotational loss, that is equal to sum of core plus mechanical loss. Then you say this is PAG, then you say this is SPAG. Then since mechanical loss you have already taken into account, you say this is then P net mechanical. I am reiterating this point. If these losses are known totally, then use this power flow diagram depending upon the situation of the problem. Okay. Otherwise, there is no one way of telling use always this power flow diagram. It depends upon the problem at hand. But anyway, it gives you a fair idea of what is the thing going on. Therefore, this is the thing. Now, why all these words I have told you before telling about the circle diagram of a 3-phase induction motor, considering all the parameters present, because the earlier case we have done obtained the circle diagram is a rather simply too simplified a thing, only R2 dash X2 dash were considered. Why this I have done is this, next time, that is this next circle diagram I will draw. So, this was the original equivalent circuit, is not? Now, in this circle diagram, what further another assumption I will do in this equivalent circuit, I will pretend like transformer with the plea that R1 X1 is smaller compared to R0 X0, I will bring this here R0 Xn. That is why I am writing R0, not RCL core loss, because it will take care of the mechanical loss as well. And then you say this is R1 and this is X1. Then this is quite familiar in transformer, and this is R2 dashed by S. See, with open circuit under no load condition I will put S equal to 0, but mechanical loss will be there. it is taken care of by this or not. Because okay, AC you make 0, keep it open and say it is under no load, transformer draws only no load current, but you cannot deny the fact in reality frictional loss is there. Who is going to supply that? Only source of input is through this port. Therefore, there must be some resistance here. That is why rotational loss we say to represent this parallel branch, and also I bring it here. Therefore, under no load condition, this circuit will be somewhat like this. These things are okay, there I am not neglecting anything, x2 dashed, and this is open, S is close to 0, and at full load condition this is the circuit, S equal to full load. So, with this in mind, we will as if varying R2 dashed by S. Okay, and try to obtain the circle diagram of the induction motor. And we will continue with this next time.